In this last video for part 1 of section 2.3, we want to take a look at using this shell method when we're integrating with respect to y. So far we've seen how the washer method can be helpful for both integrating with respect to x and integrating with respect to y, and we want to show that the same is true of this shell method that we've just been introducing and working with now. So the situation is going to be symmetric to the case in which we're looking at integrating with respect to x. We're going to start off with some functions f of y and g of y, which are continuous, non-negative. A is bigger than 0 but less than b. And R is going to be the region bounded by the graphs of x equals f of y and x equals g of y, the lines y equals a and y equals b. If you go back to the way that we started the shell method for the integrating with respect to x case, you'll notice that all that we've done here is we've replaced my x's by y's and my y's by x's. What we're doing here is with this region R, the volume we're going to take a look at the volume of the solid of revolution formed. So let's again kind of take a look at this picture and think about what's happening here. If I have some function x equals f of y, maybe that looks something like this. Remember that if x equals f of y, we're thinking about making sure that this is a function by it passing the horizontal line test rather than the vertical line test. This is still the graph of a function of y, despite it failing the vertical line test here, because it passes the horizontal line test. Likewise, we have some other function, g of y. Maybe it looks like this. And we have, let's draw a slightly better picture. And we have some a value and some b value, where a is positive and b is positive and b is the bigger value. The region R that we're looking at is the region formed between these curves. So now we have some kind of horizontal section here between these curves, between the x values of, or the y values of a and b. Cool. All right, so we have our region R here, and this time what we're doing is we're not taking this and revolving it about the x-axis. We're going to take it and we are going to revolve this region, or sorry, we're not revolving it about the y-axis this time. We're revolving it about the x-axis this time. So we get a picture that looks something like this. All right, once we've done this, what we want to do is we want to compute the volume, and again, we're going to use these horizontal slices here. And when we revolve them, we get some kind of cylinder-looking thing. Cool. All right, so we want to again talk about what is the surface area of this cylinder, and that's the thing that we want to integrate from y equals a to y equals b. Well, we know that the length of this cylinder is we know that the circumference of this cylinder is given by 2 pi times, this time we're looking at the y-coordinate. So the radius of this cylinder here, going from the center all the way out to one of its sides, is going to be the y-coordinate of the point that where we've drawn this horizontal slice. So we know that all the way around, the circumference of this thing is then equal to 2 pi times the radius, or 2 pi times y. The other quantity that we want to introduce, or that we want to think about here, is we want to multiply by the width of this cylinder that we've drawn here. And the width of this cylinder is the difference between these x values this time. Since the x values on the blue curve are given by x equals f of y, and the x values on the green curve are given by x equals g of y, then what we're looking for here is the larger x value minus the smaller x value, which is the absolute value of f of y minus g of y. All right, so this is going to be the volume of this solid of revolution that we're going to obtain by rotating about the x-axis here. So we have kind of two different ways of thinking about solids of revolution now. We can rotate them about the x-axis, we can rotate them about the y-axis. And then once we know which axis we're rotating about, we have two different ways of computing volumes. We can either use a washer method or we can use a shell method, depending on which is appropriate. For the moment, we're just getting a little bit of practice with the shell method. In part 2 of this section, we'll talk about how do we decide which method to use, and we'll sort of see some different comparisons. All right, so for the moment, let's take a look at example number 5, which is asking about the region R bounded by the x-axis, the curves y equals square root of x, y equals 2 root x minus 1, and we want to find the volume of this region formed by rotating R about the x-axis. Great, so let's draw a picture of this region first, as always. So we have, we're using the x-axis as one of our bounds, and both of these curves live in the first quadrant. The curve y equals square root of x, we know something about what that looks like. The curve y equals 2 root x minus 1, well, we know that looking at root x minus 1 means take the graph of root x and shift it to the right 1 unit. The factor of 2 there is a vertical stretch by a factor of 2, and so we know that 2 times root x minus 1 is going to grow faster than root x, meaning that at some point, even though it starts off to the right, at some point it's going to end up intersecting and growing larger than y equals root x. So in green here I've drawn y equals 2 root x minus 1. So R is the region bounded by the x-axis and these two curves, and so R is going to live right here. So the first thing that maybe we should think about doing is finding, well, what exactly is this intersection point here? So to find the intersection point, we know that they have the same y coordinates. So let's see. So we'll have root x equal to 2 root x minus 1. We can square both sides, for instance, to give me x equals 4 times x minus 1. So that equals 4x minus 4. Let's see, subtracting x from both sides, adding 4 to both sides, I'm going to get 4 equals 3 times x. And so x is going to equal 4 over 3. Great. All right, so we have an x coordinate here for this intersection point. It's 4/3, and that's going to tell me that the y coordinate of this intersection, this is some information that we're going to need to know because this is going to be the largest y value. So the y coordinate is going to be the square root of 4/3, which equals 2 over root 3. Great. Let's go ahead and add that to our axes as well. So now what we need to do is we need to think about a horizontal slice here, and we want to take this horizontal slice and we want to revolve it about the x-axis here. So again, we want to integrate the surface area of this horizontal cylinder that we're forming here. We're integrating from the smallest y value to the largest, so from 0 to 2 over root 3. The function that we're integrating should be the circumference of this cylinder that we're forming times its radius, or circumference times its length. And its circumference is the usual 2 pi y, and the length is going to be the larger x value minus the smaller x value. Well, the larger x value here is given by the green curve, and the smaller x value is given by the blue curve. But we don't yet have a formula for the x value in terms of y, so we need to do a little bit of work to solve for that. On the green curve, we have y equals 2 root x minus 1, and so that's going to tell me that y over 2 equals root x minus 1. Squaring both sides is going to give me y squared over 4 equals x minus 1. And adding 1 to both sides is going to give me x equals y squared over 4 plus 1. Great, so that gives me the x value on my green curve. I also want to know a formula for the x value on my blue curve. This one's a little bit simpler because we have y equals root x, and that simply tells me that x equals y squared. Cool. So I have these two different formulas for my x values here, and I know I want to take the larger x value minus the smaller x value. The larger x value is given by my green curve, so it's y squared over 4. The smaller x value, or y squared over 4 plus 1 rather, the x values on the blue curve are smaller, so I want to subtract away the y squared, which represents the x value there. And now I'm integrating with respect to y. All right, so we've done a little bit of work here. We've set up this integral, and now all we need to do is compute. So we want to factor out that 2 pi as usual. Integrate from 0 still to 2 over root 3. Distributing in the y is going to give me a y cubed over 4 plus y minus y cubed dy. Let's see, we can combine those y cubed terms together. 2 pi integral 0 to 2 over root 3 of, we're going to have minus 3y cubed over 4 plus y dy. And now we can actually apply our power rule here to get 2 pi times, we need to increase the exponent on y by 1, so we're looking at a 4th power. We're dividing by the new exponent, so we're going to have a 16 in the denominator, and for the other term we're going to have a y squared over 2. We want to evaluate from 0 to 2 over root 3. And so we can go through the computation now, plugging in 2 over root 3. So we'll have 2 pi here. We'll have minus 3, 2 over root 3 to the 4th power over 16. Let's see, plus 2 over root 3 squared over 2. I want to subtract away this function evaluated at y equals 0, but we know that at 0 this thing works out to be 0, so we don't have to subtract away anything at all. Great, so again here we have some kind of answer. Maybe this is certainly a sufficient answer as far as an answer to any problem goes. Maybe we want to simplify it a little bit, but certainly we don't have to. This is going to be good enough. If you want a decimal, though, you are certainly welcome to work through this to get one. All right, I think that's it for the moment. So we have a little bit of practice doing this shell method in terms of both integrating with respect to x and integrating with respect to y. And next, we want to think about how do we decide which method we want to use and which method we don't want to use.